All right, so this idea of integrals being used to find general and particular solutions has a really important um, use for us, and let's take a look at it. First, let's just remember this from calculus. If you have a position function, a position function is a function that gives you the position of an object at a given time. Most often the simplest ones we look at are those that are falling or or being thrown up. So if we have a position function, we'll use x of t to represent that, and of course it's a function of time. The position of this object flying through the air depends on the time. Remember these facts from algebra, that if I take the derivative of the position function, I get the velocity function, right? If I take the second derivative of the position function, or which is the first derivative of the velocity function, I get the acceleration function. So we just want you to remember that you've got this relationship between position, velocity, and acceleration. Of course, it makes sense because velocity is the derivative of the position function, but velocity is telling us how the position how position is changing with respect to time, which is exactly what the derivative is. It tells us how the derivative of a function tells us how that function is changing with respect to the independent variable. And likewise, acceleration, which is the derivative of velocity, is telling us how velocity is changing. Are we speeding up? Are we slowing down? All right, so I want you to remember those things. Now, how this relates to differential equations is this. If we start with this, this is the second derivative of x. So suppose we have an object on Earth, and we want to find, we know it's going to be flying through the air, and we want to find its position function, which is generally not super easy to do. I mean, the object is going up and going down, being acted upon by acceleration, by the force of acceleration, and it's also we're going to ignore friction, of course, air friction, but it's also depending on what force was used to throw that object up or to throw it down, right? So there's lots of things happening here. But let's just look on Earth for a second. We can start with this super simple differential equation, which is that the second derivative of this unknown position function is a constant, negative 9.8 meters per second squared, right? That's because we know that acceleration on Earth is constant. So look, we've started with a differential equation. Okay, so if I were to integrate this twice, I can figure out what x is, right? So let's run through that process. Let's integrate, we'll do it over here, the integral of d squared x over dt squared with respect to x is we'll integrate negative 9.8 dx, and of course the answer there, this gives us dx dt equals negative 9.8x plus some constant, okay, plus some constant. Now we're gonna call this constant, instead of just the generic c that we usually do, we're gonna use this v sub 0, right? So, but it's just a constant. There's a reason we do that. But we're one step closer to figuring out what x is. If I want to figure it out completely, we'll integrate again with respect to dx. And now we have x of t on this side right here equals, let's see, we've got to integrate this guy right here. So this is going to be negative 4.9 x, sorry, you know what, we need to back up here for a second. I keep saying integrating with respect to x. We are integrating with respect to t, so I apologize for that. So that's going to change a couple things. I'm going to just kind of override them in red here. So integrate with respect to t and t and t. And so when you get this, this is negative 9.8 t plus v of 0, and then we're going to integrate with respect to t. Alright, so just need, our variables are with respect to t. Should have known that because look, right here, right, we've got t on the bottom, so we integrate with respect to t. So let's continue here. So we are integrating negative 9.8 t plus v sub 0 dt, and that's going to give us negative 4.9 t squared plus v sub 0 t plus x, another constant we're going to call x sub 0. All right. And so what you get here is the position function. Okay. Now if we were real careful, we would and looked at this. This is the initial velocity. Okay. It's the velocity at time 0. That's always going to be the case. And this is the initial position. In other words, the position at time 0. So using, by solving this differential equation right here, we're able to find an equation that describes, or a function that describes the position of this object in free fall. Okay, and not only that, we know some definite pieces of that are always the same, and that is we've got our initial velocity, we've got our initial position. Those are the coefficients there. This actually is half of the acceleration, and in this case it's negative 4.9 since we're talking about being on Earth. But more in general, our position function looks like this: negative 1/2 whatever the gravitational constant is times t squared plus v sub 0, the initial velocity t, plus x sub 0, the initial position. And that's where we get that famous position function that we've run across and used in different places in algebra. So all we have to do to answer any particular problem with that involves this is, if we want to find a particular solution, then what we need to know is, of course, the initial position and initial velocity, right? And so we've got all the different kinds of problems that we can have. We can have an object that is dropped from a 100-foot building, and so its initial position would be 100. Its initial velocity would be 0 because it's just dropped, it's not thrown down, and we would just throw those things, those values, into those positions, and we have a working function. Again, if we're on Earth, gravity is negative 9.8. If the object is thrown up from ground level at an initial velocity of, I don't know, 50 meters per second or 50 feet per second, meters per second, be aware this constant is meters. So if it's thrown up from ground level, then its initial position is 0 because it's at ground level, and its initial velocity is plus 100 meters per second, or plus 50 meters per second, whatever I said. And then you get a working equation from that. So that should give you that gives you an insight into where the classic position function comes from and how it might be used.